They move by the millions, but rarely does anyone see them in motion. Black pigs, Iberian, large-framed, bred in forested pastures and rotational silvopasture systems, are transported across borders, across seasons, and across ecosystems in one of the most meticulously planned operations in livestock logistics. From the outside, it looks like a row of trucks. But inside each crate, a biome exists. Temperature must be stable, vibrations controlled, sounds dampened. Because inside each capsule, a living body is in constant negotiation with stress, movement, and confinement. Every crate carrying these animals is a mechanical paradox, a sealed chamber on wheels that must act like a controlled environment, yet be robust enough to endure highways, slopes, and hours of continuous vibration. To engineers, it's a moving load with sensitive biological parameters. To the market, it's a high-value export unit. To the animal, it's a small, vibrating world from which there's no escape. This is not about putting animals on a truck. It's about simulating physiological stability under dynamic, unpredictable forces. A mobile life support system in the shape of a trailer. To understand the complexity, imagine a mining haul truck, the kind that carries hundreds of tons of raw ore across uneven terrain. These machines use dynamic load balancing systems and shock-absorbing suspensions to prevent material loss, equipment damage, and energy waste. The payload isn't alive, but every bounce, every tilt, every vibration is accounted for. Now consider the black pig, a sentient, reactive, social organism that weighs over 150 kilos, reacts to stress in real time, and suffers invisible consequences from poorly managed motion. In one case, the load is inanimate. In the other, it breathes and reacts. The floor of a livestock crate that isn't properly engineered becomes more than a design flaw. It becomes a source of physiological degradation. Without dynamic damping systems, every jolt transmits directly into the pig's joints and muscle tissue. The result? Stress-induced myopathy, a condition that doesn't show up during transport, but manifests in elevated cortisol, reduced meat quality, and economic loss. The damage is invisible, but measurable. Every muscle stiffening, every shift in posture, every spike in hormone release is a cost paid long before the animal reaches its final destination. And that's the silent irony. We've reached a point where minerals and construction materials ride on shock-controlled platforms, but living creatures, bred, selected, and genetically optimized for global markets, still travel in rigid compartments, as if biology could be boxed into stillness, as if stress didn't travel with them. The logistics of black pig transport is not just a matter of distance and capacity, it's a test of engineering precision applied to sentient weight. Because if we already give mining trucks active suspension systems, why are millions of pigs still riding in crates that absorb nothing, predict nothing, and protect no one? What we're looking at isn't cargo, it's life, in motion, and it's being moved with a fraction of the technology we already use for inanimate loads. The question is no longer how to transport pigs, but how to build mobile systems that preserve their internal chemistry across hundreds of kilometers. That is the real challenge. That is the hidden engineering, and that's only the beginning of the journey. Inside the cargo bay of a pig transport trailer, temperature isn't a fixed number. It's a fluctuating landscape. In theory, these compartments operate within acceptable thermal limits. But in practice, the air isn't uniform. Heat stratifies. Moisture accumulates. Invisible thermal layers form across the length of a single crate. One pig may be cooling under a draft near the intake vent, while another, just a few feet away, is slowly suffocating in a pocket of stagnant, rising heat. This hidden heterogeneity is not rare. It's the rule, and it quietly compromises the welfare of every animal in transit. The reason is structural. Trailers are traditionally ventilated, as if air behaved consistently across space. But pigs, especially black pigs with dense subcutaneous fat and darker pigmentation, retain heat more aggressively. And when dozens of them are grouped inside a metallic enclosure, with limited airflow dynamics. The result is microclimate zones, areas where temperature and humidity climb silently, undetected, until they trigger respiratory stress, fatigue, and systemic imbalance. These are not isolated cases. They are systemic consequences of a design model that treats thermal control as a general parameter, not a precision strategy. That is beginning to change. In recent years, agricultural engineers have borrowed from another industry that knows how to manage microclimates with exacting precision: greenhouse horticulture. The result is the development of zonal cooling grids, systems that distribute air selectively through modular ventilation flaps, guided by thermal sensors spread across the trailer. Instead of treating the trailer as a single climate cell, it becomes a network of climate zones. Each one receives calibrated airflow, adjusted in real time based on heat signatures, animal density, and movement. The principle is simple: don't cool the trailer, cool the pigs. And the data confirms the shift. In coordinated studies between Spain and Brazil, trailers equipped with zonal cooling systems registered a 36% reduction in acute respiratory distress events during long-distance shipments. That means more animals arriving stable, fewer emergency interventions, and a measurable gain in post-transport meat quality. It also means fewer losses at the border. Export units that fail welfare checks are often disqualified before reaching market. A single temperature pocket can mean the loss of an entire shipment, not because of negligence, but because of invisible thermal fatigue that no one accounted for. In Castilla-La Mancha, a livestock cooperative decided to retrofit its entire fleet with adaptive air management systems. It wasn't a marketing move, it was a logistic strategy. After the upgrade, animal mortality dropped, rejection rates at processing plants fell, and the cooperative's export approval timeline was reduced, thanks to better condition scoring on arrival. For them, thermal regulation became a competitive edge, not just a welfare decision, a structural one. Because in the mechanics of live transport, airflow isn't about comfort. It's about viability. And that changes the paradigm. We often think of transporting pigs as a question of load weight, fuel cost, and route planning. But every crate is really a set of thermal cells, each with its own behavior, inertia, and risk. Miss the airflow, and you don't just affect the ride. You alter the animal's physiology before it even reaches the next checkpoint. You don't transport black pigs. You transport mobile environments. Environments that breathe, heat up, and stress under pressure. And when those environments are ignored, the cost isn't just thermal, it's biological, logistical, and economic, all at once. Before we move on, here's something that might surprise you. While engineers are redesigning crates to manage airflow and pressure, there are also innovations happening in the tools and gear used by those working closest to the animals, on the ground, in the field, and on the move. If this kind of precision thinking fascinates you, take a look at the pinned comment. There's something there we've selected with the same attention to detail this entire system demands. At first glance, a livestock crate is a simple structure. Flat floor, rigid walls, lateral ventilation. But simplicity in design often masks complexity and consequence. When the transported body is light, flexible, and inert, traditional rectangular crates may suffice. But with heavy breed pigs like the Iberian black pig, each weighing over 150 kilograms and built with compact muscle and low ground clearance, the geometry of the crate becomes an active mechanical interface. It shapes how they move, how they rest, how they brace, and most importantly, how much damage they accumulate during the trip. The problem begins with a contradiction. These pigs are bred for quality. Slow-grown, robust, genetically selected for high-value meat. Yet they are transported in enclosures designed for speed, density, and repeatability. Traditional crates don't account for the way these animals shift their mass, especially during turns or sudden stops. Their wide stance and low agility mean that even a slight jolt can result in abrasions, joint hyperextensions, or posture collapses that cascade into muscle fatigue. These are not just injuries, they are transport-induced failures, mechanical stresses applied to biological systems. That insight is guiding a quiet, designed revolution. Inspired by orthopedic flooring used in racehorse stalls and high-impact animal transport, engineers have begun introducing convex corner modules that reduce impact concentration and allow smoother pivot movements. Floor panels are being replaced with bioplastic compounds embedded with micro-spring systems, subtle, flexible surfaces that distribute weight and absorb vibration. The idea isn't to make the crate soft, it's to make it responsive. Like the sole of a technical boot, it must cushion without compromising structure. And it's working. In long-distance operations from Portugal to Germany, modular crate systems equipped with these responsive features led to a 45% drop in recorded injury incidents. The difference wasn't just in survival, but in condition scoring, the veterinary evaluations performed on arrival that determined the animal's physical integrity. With better conditions, scores come lower rejections, smoother processing, and cleaner data trails in traceability systems. The crate, once seen as a passive element, is now understood as a biomechanical environment, one that either absorbs or transfers kinetic energy directly into the animal's joints. Importers have noticed. A large-scale German pork distributor recently documented the effects of switching from conventional rigid crates to modular systems with ergonomic floors. Their internal metrics showed fewer injuries, lower stress indicators in blood samples, and more consistent behavioral recovery post-transport. In numbers, this meant not just better animal outcomes, but improved product quality, fewer welfare audit flags, and shorter turnaround times at reception sites. What started as an engineering experiment became a standard operating procedure, because once the biomechanics are respected, the entire system aligns. These animals are not sacks of grain or industrial parts. They are complex, reactive masses in motion, with blood flow, joint compression, fatigue thresholds, and memory. Treat them like inanimate weight, and the damage will be mechanical, yes, but also biological, regulatory, and financial. Treat them as kinetic organisms inside engineered spaces, and the transport system evolves from a metal box to a responsive platform, one that moves with the animal, not against it. And that changes everything, because crates are not just for containment. They are transitional habitats. They decide how much energy the animal must expend to survive the journey, and how much quality remains when it's over. In the mechanics of modern livestock transport, the crate is no longer a passive container. It is the first interface between biology and industry, and it speaks in geometry, pressure, and motion. Livestock transport has always been treated as a logistical function, a matter of distance, weight, and timing. But Black Pig exports reveal something else. Transport is of physiological challenge. Inside each crate, an animal isn't just being moved. It's being tested. Heat, vibration, density, and confinement all act on the body. If unmanaged, they trigger a chain of biological disruptions long before arrival. That's why the future of live cargo isn't only stronger materials. It's intelligent mechanics applied to welfare. In the Netherlands, the BioTrace Live initiative is redefining how this works. Each pig is equipped with biometric sensors, tracking temperature, motion, and stress. As conditions shift, onboard systems respond, regulating ventilation, lighting, and shock absorption dynamically. The trailer becomes a reactive ecosystem, adjusting itself to maintain physiological balance. It's no longer about reducing discomfort, it's about preserving internal stability during transport. The same principle applies to the floors beneath the animals. Some modern crates now include pressure-sensitive panels that detect micro-movements and adjust airflow distribution. Similar to variable-rate planters in agriculture, these systems deliver input, in this case air, precisely where and when it's needed. The result is not just better comfort, but fewer stress spikes, lower mortality, and higher quality scores at the processing stage. Traceability also gains a new layer. With real-time monitoring, welfare is no longer a guess made at arrival. It's a record, tracked hour by hour, shift by shift. Meat quality is preserved not just by genetics or diet, but by how the animal was stabilized in motion. That data, once invisible, now travels with the animal, creating a chain of accountability that begins the moment the truck starts moving. This turns logistics into a biological system. The crate is no longer a container, it's a machine that protects a living being under dynamic load. Sensors replace assumptions. Ventilation becomes adaptive. Transport becomes traceable, not just in location, but in condition. And the core lesson is simple. If stress can't be measured, it can't be managed. And if it can't be managed, what's being exported isn't livestock, it's risk. The invisible engineering that now governs these shipments doesn't just move pigs. It safeguards the biochemical integrity of an entire food chain. That's not an upgrade. That's a structural shift in how modern agriculture thinks about movement. With precision, with responsibility, and with the mechanics of life in mind. Before you go, there's something worth checking. Open the pinned comment. You might be surprised by what's there.